You've heard of AND, OR, and NOT gates, but did you know that computer chips usually don't directly use them? Instead, they run on just one kind of gate called a universal gate. Today I'll show you how using a universal gate is enough to do it all, and why that matters. Hi, I'm Oliver, a computer science student and tech enthusiast. I used to think that it was necessary to use all three fundamental gates to get computers to work, and couldn't imagine a single gate doing it all. I struggled with understanding how these universal gates work, but now they make perfect sense to me, and I want to help you get there too. If you don't know what gates are yet, or need a refresher on the three fundamental gates, AND, OR, and NOT, I suggest you check out my first video covering these beforehand. There I also introduced truth tables, which I will use in this video. The first universal gate we'll get into is the NAND gate. NAND stands for not AND. So this gate consists of a NOT gate and an AND gate. Essentially what it does is it puts the two inputs A and B into this AND gate and then passes the output of this AND gate through the NOT gate. So the behavior here is actually just the inverse of the AND gate. And we can also see this in the truth table as our output is always 1, except if both inputs are 1. Looking at the AND gate, we can see that the output, which is column C here, is equal to the inverse of this out column for the NAND. If we move to our simulation, we can see here that on the top I have a NAND gate, and on the bottom I also have a NAND gate, but separated into an AND gate and a NOT gate. These are both connected with the same inputs as the NAND gate and are connected to an output. When we switch the inputs on and off, we can see that the outputs of both logic gate systems are equal. This is one way of showing that a gate or a system of gates is equal to another one, because for every possible input sequence we have, the outputs of both systems are equal. The next universal gate we have is the NOR gate. The NOR gate is very similar to the NAND gate, as this N in front of OR means that we have a NOT after our OR. You can see in the diagram that we have two inputs going into an OR gate, and the output of this OR gate being negated, so put through a NOT gate. The circle always means that we are negating the output of the original gate. So we can fill in this truth table by looking at our OR gate truth table and inversing all the outputs. Here is our OR gate once more from the previous video, and we can see that the output is 0, 1, 1, 1. So if we inverse it, we would get 1, 0, 0, 0. And this is also the result we get for our NOR gate. Going back to the simulation, you can see on the top I have the NOR gate by itself and the bottom the OR and the NOT gate. And trying all possible combinations of inputs, we see that the output is always the same for both systems. Now, you've seen both of these universal gates, but why are they actually universal gates? Well, in the last video we've seen the AND, OR, and NOT gate, and learned that these are sufficient to do most computations in classical computing. And now, to show that these universal gates are sufficient to do this too, one way to do this is to replicate each of the fundamental gates that we've learned in the previous video using these universal gates. So I'll show you both for the NAND and the NOR gate that you can use these to build the other gates. So I'm going to start off with the NAND gate, and first we're going to try to replicate the NOT gate. In our last video, we learned that the NOT gate only has one input, and the output is always the inverse of the input. To replicate this gate using NAND gates, we use our input connected to both inputs of our NAND gate, since we have two inputs for it, and connect the output, which is only one, to our output as well. So we have one input and one output, the same as the NOT gate. And if our input is off, then our output is on. And if our input is on, then our output is off. So we've created the NOT gate. Next, we're moving on to the AND gate. Previously, we learned that the output of the AND gate is only on, or 1, if both inputs A and B are on as well. To replicate this using NAND gates, we can simply input both of our inputs, A and B, into our NAND gate, and then connect the singular output of this first NAND gate into another NAND gate, and in this NAND gate connect it to both inputs, and then have the output of this NAND gate go to the output. So now we have two inputs and one output. If both inputs are 0, our output is 0. If one input is on, or either of these inputs is on, our output still stays off. And if we turn on both of these inputs, our output is on. So it replicates the AND gate perfectly. The last gate that we want to replicate is the OR gate. The OR gate's output is 1 as long as at least one input is 1, and 0 if both inputs are 0. Coming back to using our NANDs, what we are doing is first inverting the inputs each by themselves. And if you remember from replicating the NOT gate, this is simply adding one input in both inputs of the NAND. And then we will connect the output of the NAND into this third NAND. So again, in the bottom input, we add both of these to the NAND's input, and then the output of this NAND to the third NAND. And the output of this third NAND will be our total system's output. So now you can see if both inputs on the left side are off, the output on the right is off, turning one on turns on the output, turning the other one on also, and having both on also keeps the output on. So it also replicates our OR gate. And now, as this NAND gate is able to perform the actions of the NOT gate, the AND gate, and the OR gate, we can deduce that the NAND gate by itself is as powerful or can do as many things as the AND, OR, and NOT gate can. And the same is true for the NOR gate. It can replicate the NOT gate, the OR gate, as well as the AND gate. Now we've seen that the NAND and NOR can be used to replicate all the fundamental gates, and what is even cooler now is that if we're able to show that any set of gates is able to replicate the NOR or the NAND gate, it is enough to tell us that it can create any gate. So any gate that you can create using the fundamental gates AND, OR, and NOT can be made using a gate or several gates that can replicate the NOR or the NAND. And this is very useful. You can use this to look at any gate system or look at any set of gates and tell whether they're sufficient to create all systems. Now we've learned about the NAND and the NOR gates, but why are these being used at all? So why would you use NAND or NOR gates in hardware instead of the fundamental gates? Well, it is a lot easier to use just one of these gates, say for example the NAND gate, instead of using these three types, NOT, OR, and AND. It's essentially like a recipe that you have to print on a board, and the more different kinds of recipes you use, the more complicated it gets. By just repeating the NAND structure or the NOR structure all over a chip, you're saving the costs that come with printing several types of gates on a board. If this video helped you understand logic gates better, check out my video on binary numbers. They're built on this very logic. Like, subscribe, and comment if you want more logic breakdowns. Thanks for watching.